In the fullest form, the Chinese Remainder Theorem is a theorem about the existence of solutions to many congruence equations. Many equations, many residues, many moduli. That may be a little bit overwhelming when you see it for the first time, so we'll look at the simplest possible case of the Chinese Remainder Theorem. So the simplest case is 2 equations, 2 residues, and 2 moduli. The Chinese Remainder Theorem, or just CRT for short, tells us the following. Let's say you have these 2 congruence equations, and n is our unknown. Well, does this have a solution? And CRT tells us that, yeah, well, it depends if, let's use black. If Q1, Q2, the moduli here, these are the moduli, modulus Q1, modulus Q2, are, well, these are the remainders. All right, so if Q1, Q2, the moduli are coprime, then yes, then n exists. There's a solution, and there's a lot of them. There's an infinite number of them, but they are all equivalent mod Q1 times Q2. So let's write that. So n is unique mod Q1 times Q2. Now I have to stress that this only works when Q1 and Q2 are coprime. And don't count on it working otherwise. So if you understand this completely, and you will when you finish this video, then you'll understand the complicated many equations case. That's no problem. But it really pays to look at this simplest possible case very thoroughly. So we will prove that n exists, and then we will prove that n is unique, and then we will look at an application. The first thing that we want to prove is that this n exists. And we're going to do that by explicitly constructing some n and then showing that it is a solution of those 2 equations. So let's write down those 2 equations again. So this is equation 1 and this is equation 2. And we have this condition, Chinese Remainder Theorem only works if the moduli are coprime. But you know this from Bezout's lemma. And if you don't know Bezout's lemma, well, I did a video on it and I will send it to you. I will put the link in the description box. You can watch that video. It's a very powerful lemma used all the time in number theory and in competitions. So by Bezout's lemma, there exists 2 integers. There are actually many of them. 2 integers such that the following linear combination gives you 1. X times Q1 plus Y times Q2 is 1. All right, so this is equivalent to saying that the GCD is 1. When the GCD is 1, I can always write this linear combination and I'll get 1. And if this is true, if I can find 2 numbers X and Y such that this linear combination gives me 1, then GCD is 1. So they're equivalent ideas. Bezout's lemma says that GCD is equivalent to this statement about linear combination. So using this X and Y, I can construct a solution n. Well, I will show that it is a solution, but I can do the following construction. R1Y Q2 plus R2 X Q1. So just to remind you, R1 and R2, those are the residues, the remainders here. And Q1, Q2, they're the moduli. And X and Y, well, they're the solutions here. There are some solution to some coefficients for this Bezout combination that gives me 1. Well, okay, so I construct this. It's got an interesting symmetry. I have 1 and 2 here, then 2 and 1, Y and X. All right, so we want to show this is a solution to both equation 1 and equation 2. So let's start by eliminating something. Well, I can eliminate YQ2. Look at this. You see, I have yq2 here, but I also have yq2 here. And so I can write this like so. yq2 is 1 minus xq1. So let's plug this in here. And I get that. All right, that's nice. And let's expand this out. Okay, great. So I don't have q2 anymore, so I can simplify this further. r1 plus r2 minus r1 times xq1. Now, if I take this mod q1, then what happens? Well, if I use mod q1, well, mod q1, this is 0 mod q1. So I end up with r1 mod q1. And so this is equation 1. Isn't that beautiful? So it's solved. Yes. Okay, so if we go back here, this one, good. So n solves this equation. N is rq1. Isn't that pretty? So you can already guess that the next one is going to be very similar. Okay, I write the same thing here, but now I can, let's see, I can get rid of this xq1 because I have it here. Yes, so I can use this xq1 is y1 minus yq2. Okay, so I can plug this in, ry q2 plus r2, yeah, like so, and then what? Well, this is, okay, this is ry q2 plus r2 minus r2 y q2. So I can rearrange things a little bit. r2 plus r2 d2, yeah. r1, this should be an r1 here, yeah. r1 here. So, okay. Yeah, okay, it works out. Now, if I take mod q2, then this is 0 because this is just a multiple of q2. So if I use mod q2, that disappears. And so this is r2 mod q2. Beautiful. And this is equation 2. So I can go back here and voila. Very, very nice. Equation 2 is solved. Okay, and so n is really good. N does the job. N is a solution to the system. But we're not done yet. We still have to prove something. Our job now is to prove the uniqueness of n. But what do I mean by n is unique? The solution is unique. Well, these are congruence equations, so they mean something a little bit different from what you might expect. So we mean that if n prime is some other solution, then n prime is equivalent to n in a special sense, mod q1 times q2. So this is a magic modulus, and all solutions are equivalent to each other with this modulus. Recall the two equations, our system of congruences. We'll put n and n prime into these and see what happens. So we have n is r1 mod q1 and n prime is r1 mod q1. And these two, well, we can subtract them. We get n minus n prime is congruent to 0 mod q1. Very good. Now, next one, n prime is congruent to r1 mod q1. I'm just plugging it into here. And n prime is congruent to r2 mod q2. And I subtract these two. I get n minus n prime is equal to, congruent to 0 mod q2. Okay, that's very good. And to make further progress, I need a little theorem from number theory. And the theorem goes like this. Suppose I have A and B such that they are coprime. Then let's say I have this situation. If A divides X and B divides X, then it follows from this that A times B divides X. I think this pretty little number theory theorem was first proved by Euclid. I'm not sure about that, but I think so. So this is very useful theorem, and we will apply it to what we proved up over here. Now, if you remember, we had assumed that Q1, Q2 is coprime. That's how the Chinese remainder theorem starts. And because of this and these two over here, I have Q1 divides n minus n prime, and Q2 divides n minus n prime. But since these two are coprime, I use my little Euclid type of theorem here, and I get Q1 times Q2 divides n minus n prime. Well, that's very good, because that means that Q1, Q2 is a factor of n minus n prime, and if I write this in terms of modular arithmetic, I have n minus n prime is congruent to 0 mod Q1 times Q2, or another way, n prime is congruent to n mod Q1 times Q2. And this is the result that we want. Any other solution, n prime, is equivalent to n mod Q1 times Q2. There we go. We proved it. So other solutions are equivalent to our solution n. It's amazing. But we can go a little bit farther than this, and I want to prove the following. Well, we proved that if we have another solution, it's got to be equivalent. But now I want to prove that there are an infinite number of such equivalent solutions. We proved earlier that this is a solution, so we know that as a fact. But it is easy to see that this here is also a solution. So think about it. That's an exercise for you. Why is this a solution? With, I should add, k is any integer. Not a special integer, but any integer. This is good enough. And if this is true, then therefore there are an infinite number of these solutions. There are an infinite number of them, and they are all equivalent. Equivalent mod Q1, Q2. All right, we've done it. We've proved the whole thing. Now let's look at an application. And the application I have in mind is an Olympiad style problem. We want to show that there's an infinite number of solutions among the natural numbers for this condition to hold, that this expression is divisible by 7 and 11. That's very interesting. And it's a bit mind-boggling. How on earth can we prove this? But we can do it with the Chinese remainder theorem. Let's start by using brute force. We'll look among the residues, the reduced residues, mod 7. So let me write them down. So n is 0, 1, 2, 3, 4, 5, 6, 7. These are reduced residues mod 7. No 7. I erased that quickly. It's all the integers from 0. Okay, so these are the residues 0 and up to 7, but not including 7. So if we just look in here, that's good enough. We can find a particular solution for the proposition that 7 divides 3n squared plus 2. So you go through the list and you see that 2 works and 5 works. Okay, so if you put 2 in there, what happens if you put 2? You get 3 times 4 plus 2. That's 14. Yeah, that's divisible by 7. So you see how it goes. So if I find no solution, if none of the n's work among the reduced residues, then of course none of the n's will work anywhere among any residues, okay? So that I don't need both of them. I just need one. So let's take one. Let's take n is 2 mod 7. Now that's our first Chinese remainder theorem equation. We need another one. And we'll do brute force again, brute force solution for the next divisor, 11. So we're going to brute force this. When is this true? Well, all the possibilities are here. Well, 0, 1, 2, up to 10. These are the reduced residues mod 11. So I look through this list one at a time, and I find the ones that work. And it turns out it's 5 and 6. And as a nice exercise, why don't you do this and you verify that it's 5 and 6 and 2 and 5 like I showed. And we're going to take 1. We don't need both of them. We take 1. Let's take n is 5 mod 11. And there we go. That's our second Chinese remainder theorem equation. Very interesting. So we have 2 equations and 2 unknowns. We have n is 2 mod 7 and n is 5 mod 11. Does the Chinese remainder theorem tell us the solution? Yes, it does, because 7 and 11 is co-prime. The GCD is 1. So by Chinese remainder theorem, there exists a solution. And an infinite number of them, as we've seen, but they're all equivalent. And let's use the construction to find this solution. The solution is R1y Q2, R2y Q1, and here is, let's write it here. This is R1, this is R2, and this is Q1, and this is Q2. All right, good. What are x and y? Well, x and y are the coefficients here of Bezout's linear combination. And we can figure this out by inspection. There's ways to find it when it's difficult to find it. You can use extended Euclidean algorithm, which I will talk about in a future video. But for now, let's do just sort of intuition. If we choose x is 8 and y is -5, that works. We get 1, and you might find a different solution, but this is good enough. So now we can plug everything in, and we can calculate n. 2 times -5 times 11 plus 5 times 8 times 7. When you work this out, it's 170. But all solutions are equivalent mod Q1, Q2, and that's the same as mod, what's Q1, Q2? 7 times 11 is 77. And that, if we reduce it as much as we can, it's 16 mod 77. So all solutions are congruent to 16 mod 77. And what does that mean? Well, we also proved that any solution, any number congruent to 16 mod 77 is also a solution. So all numbers of the form 16 plus k times 77, that's this. Okay, so all numbers of this form are solutions. And since k is an integer, any integer, that means that there are infinite number of these n's. Okay, so we did it. We proved that there's an infinite number of n's for which, well, let's see, I can write it over here. Infinite number of n's such that 7 and 11 both divide 3n squared plus 2. Very beautiful proof. It's a surprising use of the Chinese remainder theorem. I'm sure you weren't expecting it. Beautiful, beautiful proof. I liked it very much. Very beautiful. All right, so I have enough room to do my send off. I can let you go now. If you like this video, click like and subscribe. I am planning to do more stuff with Chinese remainder theorem. There's some very interesting Olympiad competition problems that use it in very creative ways, and it's worth knowing about. It's something used in computer science also, and it pops up everywhere. It's very good to know the Chinese Remainder Theorem and to know it deeply, like we looked at every aspect of it in this video. All right, I will see you next time.